Yeah. So audible? I'm audible. Okay. Oh, so let me start by doing by summarizing some of the main points which is about the last two lectures by Debangshu. I think Debangshu is not here. Okay. Oh no, he will not be there.
He will not be there.
No, he will not be there today. I mean, there's a meeting. Okay, so before that, just if anyone want to ask any question, please use microphone. Otherwise, I can't hear you. That's just one. Yeah. Okay, so.
Wait for some time.
Sorry?
The board behind.
Okay. This one. So, oh yeah, sure. Okay, so up to now, Debangshu has introduced like modular theory, and he has introduced Tomita operator, which is S, and he also introduced the modular conjugation operator J and the modular operator, which is delta. So, so far he has introduced this thing, and all these things is actually state dependent operator by definition. Because by definition, it only acts on some state, and it was defined by action on some. Hi Debangshu, so you will be here, or okay. Anyway, also he has stated the main point is that he's in his first lecture about the Tomita-Takesaki theory. So he has mentioned last time that and it contains two important points. One is that this modular theory has an modular automorphism, which is that like delta so this modular operator actually provides an automorphism of the algebra. This means that under the flow of this modular operator, in any this algebra, this algebra becomes this. I mean, there's a one-to-one map between. I mean, this algebra remains within this algebra. I mean, okay. So I mean, it has a one-to-one map from the algebra to itself. So it is an automorphism. Okay, and another vital point is that he also described that the modular conjugation operator, the action of this modular conjugation operator is an isomorphism from the algebra to its complement. So this is a remarkable property, like because using this modular conjugation operation, you can actually map any algebra to its complement. I mean, to its complement region. So using this left region, using to any like a linear left part to you can get the right part of the algebra just using this modular conjugation. So if you construct this algebra, you can also construct the the commutant of the algebra. Okay.
This S, so this S, what is the redeemability? Is it still real or?
Yeah, sorry, it is real. Yeah.
Why do you say it's a very remarkable property? Because J seems to be like some green function, no? Which can take you from left, right, or.
Yeah, but this is an unique operation. I mean, because okay, so no, but what other operator like do you construct like? I mean, this is a unique operator that that maps A to A prime. I mean, any algebra as you said, like in Riller space, you can take any operator and it can go to this. I mean, is there any other operation which can do this? I mean, is there any other map? No, but
is dependent, right?
Green functions do that.
Hmm?
It's
Green
like CPG kind of.
Green?
Some green function operators, something like that. Or maybe I'm thinking about it wrongly. I don't know.
Yeah, but it is saying
See,
that
Green's
like
functions are usually in a
not
causal
only-
patch or something.
I mean,
J's are anti-unitaries.
yeah, it's of course this is an anti-unitary operator, but I am saying like if you not only this problem, but if you consider any algebra of any local region, it can take to the
Okay, I'll maybe ask you later again.
Yeah.
Thank you. Go on.
So
I mean, it has been used to in holography to, I mean, some by Raju and some other guys as a mirror operator which can take from exterior to interior, etc. So it has some other use. I mean,
Yeah, so I think one remarkable thing is that it is not taking you to any, like, just the commutant of these, and not necessarily anything which is outside both of these.
Suchetan,
So that's the thing I think, because if you divide the regions, there will be a commutant of A, and other regions. So typically, I mean, the general operator may take it somewhere else, but it's precisely taking you to other regions.
Suchetan,
yes,
here. So you said J is unique.
J. Yeah, provided the S, then J is unique. I mean, if you have the S operator,
Okay.
and then
Okay,
that's
okay,
as Debangshu has said that it's a
Mhm.
unique polar decomposition. So third,
which does this?
sorry.
So many J's, right? For every state, there's a J. Like every cyclic state, there's a J which does this.
What?
Like I'm saying, for every J is state dependent, and hence there are many J's which will take you from A to A dash, right? J is not very unique.
Once you have fixed your cyclic separating state, your J is fixed. For every cyclic separating state.
For every J means?
Every state there is a J. I thought like there is J is not.
He said that if you fix S, then J is unique.
No, I
Let me ask this: like I randomly choose some anti-unitary operator which doesn't have
no,
a.
I mean, yeah. So okay. So the point is that S is these are state dependent operator. So you have to choose this particular state. Like as you said that S is psi, like A dagger psi. So for this, so S is dependent on that particular psi, and for this given psi you have a unique J, right? And that J can I mean if A belongs to A, then this J can map from A to A prime. For
So
a
I
particular
should
state. Of
so
course
so
it is
I
state
should
dependent.
think of every cyclic state as two data, like one J and one delta, where every cyclic state defines an automorphism
Of
within the group, and
Hmm.
a J which takes you to the other
Okay.
algebra.
But for a
right?
given cyclic state, it has unique. I mean, I'm saying
Yeah, but okay.
like if you have vacuum, then one J. But for yeah, so not only state but also for the region. I mean, for the algebraic region. Yeah. I mean, this S depends on the region. I mean, on the suppose. I mean, if this algebra is constructed out of this particular region, suppose it's U, then S also depends on U, particular that region, and also the state psi. So it is not only just state dependent, but also the region of where the algebra lies. It also depends on where the algebra.
So is it correct to say that if you have any arbitrary element of A, you can, using delta and J, you can get any element in the algebra of A union of A, or in the algebra A union A complement.
Please repeat again.
So let me take an arbitrary element
Okay.
in A.
Hmm.
Now, can I get arbitrary element in A union A prime using using the action of delta and J?
Any arbitrary element. Okay. Yeah. So. No, that I'm not sure.
Can I just
I was
comment?
not
Like,
about- I don't know.
can I comment?
Yeah.
Couldn't be, no, because there are as many deltas and j's as there are cyclic states, right? And then you can then if you want to go to every, starting from one element, if you want to go to every element in A itself, you need as many cyclic states as elements in A. But then to go to every element in A dash, you need as many cyclic states as elements in A dash.
I'm not able to follow, but we can discuss
Okay,
it later.
sure.
Suchetan, when you're writing it like that, so that is full algebra, right? Like
Yes.
yeah, that clear shot, right? See, the point is that in first equation, so if you apply that operation, whole algebra maps to itself.
Yes.
So the thing is, using delta, you just remain in
Every
that. So
element.
every element will
Yeah.
go to some element in that.
Yeah.
Second is using J, because there is this whole algebra. So any element of A will go to its commutant, which means every element of A can go to every element of another element of commutant of A. So that I
Yeah.
think answers.
Okay,
Yeah.
That's a nice example. Yeah.
Guaranteed that it can cover everything. That is the point of the question.
Yes.
Everything meaning?
I mean, how many A's are there in like in this, let's say in a small space, there are some number of A's, but its complement has more than operators than this small. Then how do you go from A to like the primes? That's not possible, right? So the thing is like so this automorphism.
I understand.
Might not be one.
Yeah, that's the question
Yeah, yeah,
actually.
yeah.
So this automorphism only valid for this region you are considering. When you are going to the complement region, this automorphism is not there.
No, I mean.
Yeah, there may be more operators.
Yes, of course.
Yeah, so you cannot.
Yeah,
This
yeah,
automorphism is
yeah, I
defined
get
only
the
for
point.
that. Yeah, right.
Yeah,
okay.
I get the point. Like
Yeah. That's the thing. Yeah.
So this operation on the left hand side will not cover all of A prime, all elements in
Yeah,
A prime.
yeah. In the complement set, right?
Okay.
Yeah.
See, it's not obvious. It's not obvious because you have reach leader. You can make everything in A dash from A, right? That's what I thought. Like reach leader says. At least you can make every state.
No, the state. That is about state. Right?
You can make every state from.
About state, not the algebra.
State. It's about state.
But
not
so it's
algebra.
not very convincing that you can't make everything in A dash. But naively, what he said is like what you should think. You shouldn't expect.
Yeah. I agree to that. Yeah.
The question is whether you take element in A cal, and you take it by some flow or by some conjugation to any other element in A cal union A cal prime. Calligraphic.
No, just for an example. Suppose even this case, I'll come to this later, but I'll just for this argument, I'm just saying that for the Riddler case, we know that the boost generates the modular flow, right? So for a given boost, this is a boost. So there is any element this, and this can go to for this particular flow. It can goes to anywhere, right? This is a geometric flow, right? It can go anywhere. But he's saying like that if any but this element cannot go to there. I mean using this boost, right? Particularly, yeah. So but for suppose if you want to construct a point at this region, then you have to construct some boost in
Along that, yeah, that.
which flows this line, right? So that is true that not using this I am not get a one-to-one map of every element to every other element. I mean I'm not constructing full algebra using this. It is just saying that a map. Yeah, he's right actually that it is constructing a map which automorphism that actually map the algebra to itself. That's the point. It does not cover the full algebra or something like it does not construct the full algebra using this. Because I'm just saying that like if you consider just the modular flow of this Riddler case, so using this, so I'll come to this later. I'm saying that in the Riddler case, this boost actually generates the modular flow. Okay, and so using this for a particular boost, you can go from one point to another point, right? But from this point you cannot go to this point. I mean any operator in this point, right?
In that
for
figure,
this.
In that figure, what is your A?
Huh?
You're
A.
using the boost
Yes.
But what is A then? I mean,
Oh, A is the full, yeah, of course. A is the full line. I mean, A is the full line. But I'm saying
that is the interval, but this algebra.
algebra. Yeah, algebra is lie in the full, this is the full algebra.
Set of operators you can
Yeah, in the full algebra.
So,
I mean, there is not one-to-one map that you can get any point to any point here. There, I'm saying that you can get this point from some other point. I mean, it just takes a map from this any point in there to in this slide. This is the point that you are this flow cannot. I mean, cannot leave. I mean, cannot take you outside this region, outside this A. That is the point. That's the point.
cannot take you
Outside A.
That is the statement.
That is the only point. I mean, it does not tell anything about that. You can create all the points in the A using this assessment. This is not. I mean, it should be better to things like this. I think, or sorry, I mean.
No, sorry. Automorphisms are one-to-one and on-to, right?
Huh?
Automorphisms are always one-to-one and on-to. It's like homeomorphism, for example.
Yeah.
So it should always map the whole algebra to itself, and it should be invertible.
Yeah, it is. Yeah, I'm saying it is about the whole algebra to itself. But I'm saying that suppose if you consider one particular field, so that field does not. I mean, it also. I mean,
some other field, let's say.
Some phi field. Then after this map, it goes to some is phi x to it maps some phi of x prime. Right. So
Right.
it is some x prime which lies inside this wedge.
Correct.
But I cannot take from using this map from any x, this particular x to any x prime, right?
Operator, Suchetan, the operators that you have in the set, those are actually integrals over phi. They cannot be the phi's anyway. So when you're saying flow, so maybe you can think of it as a set, that in the set there's all these boundary operators. Then you can flow in among them. That is modular flow. My question was, within this set, you have this set and another set A cap. So it seems as if using J you can move among the sets.
Yes, of course.
And using the delta, you can move anywhere within this set. So from
Yes,
one point, each of these points is a bounded operator. You can go anywhere, it seems. And from using J, you can move to the other set.
Yes.
So it seemed. So my question was whether you take any point in this A. Can you move to any point in the combination of these two, the union of these two, using flow and the conjugation?
Using J and delta.
So the statement that you have written, it just says that if you take J on the whole algebra A, you will get A prime. And within, if you evolve using delta, you will stay within the set. So that doesn't guarantee that there is a flow existing from one point to any other point. So that there could be cycles, small cycles. For example, you take one set, you take one point, and you do whatever you want, you return to that. So periodicity, and you won't be able to reach anywhere. So those kind of things could happen. So my question was in that stage.
Okay.
So in that case, even though this is true, that is you can't cover everything.
That might be true. Makes sense. So your question is that by using delta and J, can you cover full A union A prime? That is true. Yeah. Yeah, that might not be true. Yeah.
Yeah. So I mean, I was asking whether it's.
Yeah. So another important point which was discussed by Debangshu is that he has proved that that particular this operator, I mean this delta to the power iz acting on A psi is holomorphic So it is important, and we'll use this to in some case, in our case, like in the infinite dimensional case, and and the other things like he also proved like okay. So then he actually he discussed the finite dimensional case for each the Hilbert space where factorizes into left and right part, and for this case he actually showed that the delta delta actually retains for written as rho 1 cross rho 2 inverse in terms of density matrix, and delta psi 1 suppose, and delta so I'm just summarizing this.
You mean delta A is used by?
What do you mean delta A psi is holomorphic? That's
Delta.
I think
your
you wrote
IZ
expectation value, right? Expectation value.
Yeah, I mean, no, he said that it is holomorphic means that,
No,
yeah, I mean, it is also bounded in this region. I mean, in that case, expectation value, yeah, of course, he said that it is holomorphic in the expectation value.
But I remember yesterday he was taking expectation values, no? F of z. Oh, okay.
It is for any state, right?
Okay.
And then he also discussed the relative Tomita operator, which is like S psi phi. And then he, say also that's the monotonicity of the relative entropy also discussed. And in the finite dimensional case, this implies that and also from this he also discussed like strong subjectivity and the for the bipartite and tripartite system, etc. So all this thing it has been covered by Debangshu in the last two lectures. Now the today I am going to find the the real quantum field theory system. Okay. So for this he has used the finite dimensional quantum system where the Hilbert space is factorized. And the interesting or the remarkable point is that like this delta, what he constructed in this delta psi, which is like rho 1 cross rho 2 inverse, which means like in terms of density, I mean in terms of modular Hamiltonian, which is like just e to the minus kr minus kl, okay, or which is defined as minus k. So this delta is actually e to the minus k, and which k is actually the kr minus k, or rho which is e to the minus kr minus k. So for for finite dimensional system, it is true that k is actually basically kr minus k. Okay. Now what I am showing this time, that even for infinite dimensional case, like in QFT or half-sided and QFT on the half line, for this case we can also construct this modular operator using two ways. Like first I'll briefly discuss the path integral way. Okay. So
You can use that, right?
oh yeah, sure. So first I will discuss the path. First I am doing this using path integral approach, and I will briefly discuss this, not because you will see in many references like in the real case path integral, and then I want to discuss the approach by Bisogno and Wishman. So this whole thing I am just following the Witten's lecture, and yeah, but he also does sketch a proof of this theorem that the delta to understand delta and j. Okay. So first let me discuss path integral approach. So we have the system like what I am describing, that this is a half space. I mean, x1 greater than 0. This line is our space, and we want to construct the delta and j for this line and for this algebra and this. And for path integral approach, we also assume that h is actually factorized into hr cross ha. So, but we have to assume this to understand the path integral approach. So I'm just going through the main things.
Suchetan, like, are you saying there's something off with the path integral approach? There's something wrong with the path integral approach that you have to do this?
Yeah, because I have to use this in the path integral approach, because when you path integral approach, I am using the fact that this rho, I am using the fact that this delta is actually rho 1 plus rho 2 inverse, and I am computing this rho r, I mean the reduced density matrix of R, reduced density of L. Okay. So to compute this, we have to use the path integral approach, and for to use this we have to we have to factorize this Hilbert into right and left part. But
that means like factorize the boundary conditions on the path integral, right? The fields could, I mean, no,
feels
like,
good.
No, feels good. I was trying to say something. Sorry. I'm trying to understand, like, fields are like algebras, like, or you think of fields as states, like what why is it that this path integral means this?
Yeah, I'm saying that because so as it was discussed, like, so vacuum state is, I mean, we can define a vacuum state using path integral by just like d phi with some boundary condition like tau equal to minus infinity. So okay, okay. So this picture, the vacuum means actually, so okay. So this is right? That vacuum is the path integral from minus infinity to, you have to integrate over minus infinity. Now, if we construct the rho of R.
Suchetan, sorry, I'm a bit having trouble understanding that equation. So path integral always computes the overlap between states.
Overlap, but it has some psi and some phi, like, of course, but I'm just cutting this psi, I mean, by I'm imposing some, I mean, what I'm saying, I mean that, what I said.
I'm just saying right hand side is a number, left hand side, how can that be a state, like?
Of course, I'm sure, but I'm just saying that you have to take some, okay, I mean, you have to same some boundary condition on this line at tau equal to 0.
Even then it's actually right. How can say it to be a vacuum in the phi reference? You normally integrate 0 to x, no?
I mean, it is true that it should be some psi, and that psi should lie in the tau equal to 0, sir. I mean, 0. So rho r of 2, suppose Okay, so rho r means that this just this is just the omega omega. I mean the density matrix, but we have to trace over the left part. Okay, so we just integrate over the all the phi left part of the phi, and with two phi r and phi r prime, two different phi r and phi r prime. So this in the pictorial this means like and this minus infinity plus infinity. But the interesting point in the half space is like that you can have another quantization without, I mean, we are quantizing here in the time, right? But we can also use another quantization which is it's called angular quantization. Suppose you are not doing the time. You said that angle is your time. Okay, I mean you was just going from plane. I mean this Minkowski's place to some polar coordinate, right? Like from r cos theta and r sin theta. Then theta is your time. I mean you said that this eta is your time. So because you know that in Riller metric this eta is actually the time. In the Euclidean Riller metric, this eta is actually your time. So if you quantize your if you do your path integral in this angular in this angle where I mean this angle is your time, then you get some waves like this. Okay. So let's just call it some w eta. I'm not going what is w eta, but so I mean you can do this type of angular quantization in this path integral procedure, and what we'll get at the end, you will get that this this rho r okay. So okay, I'm saying before that and just so these actually generates a rotation, right? So this generates rotation. So you will get what is the corresponding conserved charge due to rotation, and that is the boost operator. I mean Lorentzian case, that is the boost operator. So so just let me define just the boost operator. I mean boost of the right wedge, which is just so these are the two. I mean, in the pictorially, this just what I'm drawing previously, that this KR means just a boost operator this way, and KL is just a boost operator this. Okay. So KR generates this, and KL generates this. Okay. And if you define another thing K, which is KR minus KL. Which is basically and it is over all x. Okay, I mean just t equal to 0. So it is x minus infinity plus infinity. So and so this actually gives the picture like this. So okay, I mean so K actually generates. So under K, this under the k operator, suppose if it is a t equal to 0 slice, so after some t after some t equal to some s, this under the flow of this k, this goes to this way and this goes to this way, because it is kr minus kl, because kl is this direction and minus kl means this direction. Okay, so it just move this OH, any constant time slice into this way, from in this way. Okay. Now I'll come back to so it has, and it is all, of course, on Tx plane. Okay, one is T and this x. Okay. And we know that any Lorentz boost so if okay, so if eta is a boost parameter in Tx plane, then the rotation it is I eta in the rotation, tau x plane, okay, in the Euclidean plane. So basically this OH, what I am defining this W eta, this basically it is actually e to the power minus k.
Suchetan, there in that diagram, both the flow are in the same up direction, or in the left side it will be in the opposite?
Louder.
In that diagram, the TR diagram, on the right hand side you have the arrow on this direction.
This direction, yeah.
Yeah, in the left hand side also it will be in the same direction.
Yes. Because I define KL is just minus of this.
Okay, I see.
Just
Okay.
minus of this. So
Okay.
Because I want to this K actually gives. So in K is in right edge it flows this way, and in the left edge this way.
Right. Okay. That's
for
how
K.
it will come. Okay.
So as I'm saying that we can also quantize this in this tau plane, where this W eta is the conserved charge corresponding to this, and so for so this means that rho r is basically 2 pi kr. So because in this picture rho r is basically, so if you want to this is rho r, right? So if you want to consider rho r's, you have to give a 2 pi rotation of in this way, right? So from if you start with this and you want to rotate it 2 pi, and you end up here, right? So this basically means the rho r is basically minus 2 pi kr. It is a 2 pi rotation of the boost kr. Similarly, rho l 2 pi k. And if we use the what Debangshu has showed in the previous day, that delta omega should be in the factorized case, it should be rho r cross rho l inverse. Then this means that it is 2 pi here minus scale. So here, so this is minus 2 pi k. So this case is basically k r minus k l. So what we defined in the first class as the total modular Hamiltonian. So this k is the total modular Hamiltonian, which is just the difference of right and left modular Hamiltonian. Okay. Now let me see what happens in the S, delta, and J. If we assume delta is, as we see that delta is should be this, right, from this picture, from this path integral picture. Now, so this from this picture we see that if we consider delta omega to the power half a omega equal to some a tilde omega, where a belongs to upper and so from this picture you can see that if you delta to the power half means it is to the power minus pi k, right? So the minus pi k means that it is a pi rotation. So from here you just so if you start from here you just give a pi rotation. So you just from if you this is the edge, so you if you start any operator from here you will get an operator here in the Euclidean plane, right? On the traverse. So in this way, this actually belongs to this a tilde actually belongs to a so the action of this actually belongs to some operator which belongs to the left edge, not in the right. Now so take two field phi and phi. Let take one field phi, which is a scalar Hermitian. So what is the action of phi? What is the action of S on phi? Okay, yeah. Okay. So as we know that S A omega acting on omega is basically a dagger omega, and since phi is the Hermitian operator, so this is just same. It should be just phi omega, right? So 1 point. 2 is like the action of S omega on phi dot. Phi dot means d phi dt. So what is this? That okay? So it is the phi dot is the time derivative of phi. So if origin the time derivative is in the like future like in the right edge, then after the pi rotation, it actually gives the downward in the left direction, right? If it is the up in the right direction, then it will be down in the right direction. Okay. So this means that this phi dot there will be a minus of phi dot. Oh sorry. I just tell a minus x comma y because in the it is a minus x. So these two things you just get from this path integral picture. Now using this fact, we also get two conditions on phi and phi dot. So delta so we'll see that any operator A, it just go to L tilde. A tilde belongs to the left edge. So action of this basically phi 0 minus x and y. right? Now also the derivative of this is just oh sorry, I just sorry one there should be no minus sign, okay, because it's just okay. So no, sorry, I write some mistake, but there should be no minus sign because this is just the action of A acting on A. It's just A dagger. So A dagger is just phi. I mean, if phi dot is also Hermitian, so phi dot is also there should be no minus sign. Even there is no minus sign. Sorry, I just write some wrong things. There should be no minus sign because
But A tilde belongs.
no. I'm just saying A's. So okay, I'm just using that A's. A omega is A dagger omega. A is the phi.
Suchetan?
Oh, acha, S.
A is the phi. So just and A is the phi dot. So in both cases, it's just phi dot same and the phi is same. But for I'm sorry for my mistake. But for delta to the power half, this stays the left way. So there should be a phi of it is, and for phi dot it is just minus phi dot. Right.
Suchetan?
So this minus sign comes from the fact that this under this pi rotation, this future pointing any vector goes to the past pointing vector. So if it is outward in this time derivative is outward direction, then after pi rotation it will be minus downward direction. So there is a minus sign. So now from this two fact, we know the action of
Hey
A
man.
and action of delta.
Hello.
Delta half. Yes, sure.
Could you explain from this point? So I think I lost you there. So delta raised to half acting on A omega. So wasn't delta supposed to give 1 on omega? So now you have A omega. It seems as if so A omega is some so can you give the argument for why this is the case? So
No, yeah, I'm just saying this, since in this case delta is a boost operator, or in the Euclidean plane it is a rotation operator. So delta to the half, let's 2 pi. So delta is a full 2 pi rotation, right? 2 pi of boost. So delta to the half means pi rotation. So in the Euclidean plane, the pi rotation means you are in the right wedge to the left wedge.
So A omega is supposed to be a state. What sort of state? So what
omega
is
is the vacuum
little
state. Here
a?
I am all considering the vacuum state. A is the operator which belongs to the right wedge. Okay.
Okay.
And the algebra of the right wedge, and after this delta to the half, since it gives a pi rotation in the tau s plane, it goes to the left wedge, which is where the element of A tilde belongs to the left wedge. That's the fact.
Okay.
So we just use the property of S and property of delta to the half here. So from these two, we can also see what is the property of J in this case. Okay. So since S is just like J delta to the power half. Yeah. Oh, sorry. So from these two, we can get the action of J on phi and phi dot. Okay. So you can see why this is true, because you just act S on phi, S on A phi, I mean S on phi omega. You'll see that S on phi omega gives phi dot. Sorry, this gives just phi, and but S is just the j delta to the power half. Okay, so now we see that from delta to the power half acting on phi is just this phi 0 minus x minus y. So this is actually j phi 0 minus x minus y. This is phi. So the action of j of phi must be like this phi 0. So another minus sign will be required to get plus sign, right?
Yeah.
So action of j on phi is like this. Similarly, in the same way, if you see the action of phi dot, action of j on the phi dot specially gives that this.
Suchetan, I have a confusion. Like you're getting this minus on phi dot because your dot is with respect to Rindler time, not the flat space time, right? If your the dot is with respect to flat space time, there shouldn't be a minus sign. Is that right?
No, it is t means just t.
The flat space time.
Flat space time.
So then why are we getting a minus sign again?
Here, I mean here.
Yeah, here, yes.
Yeah, because it is just saying that the under the rotation. Suppose
the time which flips is the Rindler time, not the flat space time. No, flat space time will be upward on the right side and left side.
But after the rotation, I say after the rotation, pi rotation. If
this I'm not able to follow.
Then after you will, I mean, so this is a plane, right? Tau x plane, and you are saying this anything. Suppose there is a vector.
But the rotation is done in the Rindler time, no?
No, rotation. I'm saying the Euclidean time. Okay. So I mean,
what?
I mean Euclidean tau x plane. The rotation is the tau x.
Tau is the Rindler time, no? No, tau is the Wick rotation of the Rindler time, right?
No, Rindler time is eta. I mean.
And the thermal state is obtained in the Rindler time, right? For the Rindler particle, Rindler observer. Hence, the Wick rotated time is Rindler observer's time, right?
No. Okay.
What are you saying? So that I thought in the left, his argument is on the left wedge. The time is on the opposite direction, but that is a statement about the Rindler time. The flat space time is upward in both the wedges.
Yes, that is both the wedges. But I'm saying that after the rotation.
Which rotation? What rotation? What is that? What is that? That's doti or doita? But you rotate in doita only. Why is that?
But I'm just saying if I just directly rotate it. I'm saying dou t is pointing upwards on the left, but this vector if you rotate it with eta it's pointing downwards. So
Is it? I don't understand that either, but okay.
I mean at least from what he said that's what I mean I'm saying that he's rotate it just draws a circle around the origin.
And then you just bring it like this.
Yes. That is what I'm saying.
Supposed to be pointing upwards, but there is looking like it's pointing downwards, so you need to multiply with the minus.
Your rotation is also, of course, in the, I mean, what you are saying in a real time, but I'm saying that any time derivative in the this time, I mean, Minkowski time, that would be reversed into this way after the rotation in the real time.
That depends on how you rotate it. I could have taken it like this also, which is what you did, and then it will come like, I mean, I'm not able to.
So eta is in the regular ways, right? It's only this. My guess is if you do the Wick rotation, I think you get it just goes completely. This I'm assuming that's what happens.
So is the dots are with the Minkowski time is what
Yes,
you're
yes,
saying,
yes, yes.
and that gets a minus
The
sign.
t equal it is dot means t phi dt. T is the Minkowski time.
Can I just confirm this? Is it because del t is not the real Hermitian thing, but I del t is the Hermitian thing, and then you get the minus sign because of the I? If you say that, maybe I will understand, I think. Because there is some antilinearity or something, maybe not. Sorry. So maybe in that case, SS would get the minus sign, not the deltas. But initially you wrote something like that, no?
Phi dot is not Hermitian. I mean, okay, phi del t is. Phi del t is.
With the S formulas, not the delta formulas, then I think.
Okay. Or I'll think about this. I'm not sure. Yeah. But in Witten's note, it was argued in this way, like any future pointing vector will be after rotation, it will be in the past direction after the action of this delta half. So
Dot that makes sense if dot is the render time, no? That's what I thought, but then you said it's
no,
Minkowski.
I think it is del t. I'm sorry.
Okay.
See, it is anyway pointing downwards there during the actual movement, right? But
Because yeah, it is del t. I mean,
I'm saying because it's t is pointing upwards there, whereas eta is pointing downwards. That's why you have this minus sign. Whereas here both are.
yeah, that was the only thing.
What I'm saying is, like, what I thought is naively, phi dot is the time derivative of the field. Operator acting on the right wedge.
Yes.
Now you want to make the phi dot on the left wedge. Okay? So you just apply with delta and you get it. But now you're saying you have to put a minus sign. But then I thought that's because you are converting phi dot in the right side to the Rindler time. And then you take it, actually you should have done it in the Minkowski time. Then you get phi dot here and phi dot here. But if you are doing in the Rindler time, you get phi eta here, phi eta, but with minus sign now because phi eta flipped or something. That's what I naively thought.
It was in Minkowski time. That was I'm sure.
Yeah, I
sure
see.
that phi t is a Minkowski time. I'm pretty sure. Yeah, but the argument is that, like what Anish was saying, that the future, under this rotation, that yeah. Okay, so if these two are correct, then J must be this. J must follow this relation, right? We want to. So from these two, we can see that J is an anti-unitary map by definition. Which anti-unitary operator, anything, but which map x2 minus x, t2 minus t, and y2 y. So and so in QFT, so you are agree this point. That's J, the action of J in this, right? If S and delta half is satisfy those two relations, the J must satisfy this relation. So from this we can see that this action of J on phi is just phi is just reversing the x at t equal to 0, and phi dot it reverses since it is del phi del t, so it reverses the t goes to minus t, so it is minus phi dot, and x goes to minus x. Okay. So in QFT and unique anti-unitary operator which take this map is called the CRT operator. So C means charge conjugation, R means the reflection, which means that x goes to minus. Just CPT means the parity for all coordinate goes to minus. I mean, if x and y both goes to minus x minus y, then it would be parity operator. But this is not this is not the case here. This is just going y goes to y, but x goes to minus x. So this is called R, reflection operator, and t is the time reversal operator. This t goes to minus t. And he also said that yeah. So and it is an symmetry in any dimensional QFT. I mean, yeah, but CPT is symmetry in the only in even dimension QFT, but CRT is true for any odd or even dimensional QFT symmetry. Okay. And so why it is C, why charge why C is there? From there you cannot see the what is the role of C. But if you construct suppose a complex scalar field or two scalar field with SO2 or you say I mean yeah with SO2 symmetry, then the generator of charge is basically I mean then the generator Q, the charge is this thing. Okay. So this follow from just if you consider the complex scalar field and consider the charge, and for this you can see that under CRT operator this phi 1 goes to and the phi 1 and phi 2 dot under this action of J, this become minus and this become plus, right? So these are overall minus sign. So Q goes to minus Q. So this is the role of charge conjugation. So in this case, it is clear that this is actually CRT operator, not just RT operator.
Just to understand, like just to understand, when you write this, when you want to use like some type of Rindler decomposition, you lose the normal rotation symmetry, is it? You don't have it anymore.
You don't? Why?
The normal rotation, SO3 rotation that you usually have in a field theory.
Okay. Yeah.
Do you don't have it anymore?
No. Yes, we have.
So then the reflection is just a rotation, right, in the z-axis?
Rotation in the okay.
So I can go to, if I'm not changing y or z, if I just want to go from x to positive x to minus x, I can just rotate about the z-axis, right? I can go from plus x to minus x.
But you are just rotating x to minus and t to minus t, not the other.
No, parity you are doing all three. It's a change of the full left-handed versus right-handed. You can't do it under rotation.
Yeah, but if you have the full SOD, I mean, then you can also rotate the y goes to minus y, right? I mean.
Yes.
Yeah, but that is not present here. I mean, it is an unique operator that only just x goes to minus x.
So that's nothing. So you are saying that you don't have rotation in this when you write it this way, when you do this Rindler decomposition or something.
No, why we don't have rotation? No, I am saying that the action of one anti-unitary operator, right? J is some anti-unitary operator which has this symmetry, and that is CRT, right? That is one operator that is CRT which is anti-unitary operator. I mean, there is a time reversal symmetry which is anti-unitary, and also this. I mean, no.
So you're just calling.
Not rotation does not. I mean, just rotation is not an anti-unitary operator, of course.
No. I'm just saying that x going to. So I mean, maybe I'm misunderstanding. Like, yeah. I mean, like CPT operator has a. I mean, I cannot. CPT is unique, like in the sense that each C, P, and T I cannot get from anywhere else. But this R I can get from rotation. That was my.
But a very specific rotation.
Yes, but some element in the.
That means, so if it is a symmetry, it should be for all of them. Yeah, so if it's just rotation by pi.
No, but I can. It's a finite transformation of rotation.
symmetry, you'll have to use all the elements, right?
Okay, maybe I'm not understanding.
No, but
No.
I'm saying that we want to construct one anti-unitary, unique anti-unitary operator which have this property. That is only one. That's
Fine,
CRT
fine.
operator.
J having that property is
Yeah.
fine. Okay, I just thought, okay, maybe CRT is some independently there is something definition of what CRT is or something. That was my confusion.
But rotation is connected. I mean, it is a.
This is also, I mean, I can, it's a fine, I mean, if by that logic I can say that if I rotate by 22 degrees, then that is not a rotation element, that is a discrete transformation. I mean, I'm rotating by pi.
You have to check the determinant of this transformation. If it is -1, then you know it's not a
No, C and T is fine. R is, huh? It will be positive. I'm rotating about Z axis by pi. It will
But
be cos
CT is
of
not
minus
an- I mean, I
that,
don't
so
know.
it will be positive. It won't come as minus. I mean, in this setup, because of C and T, it will be anti-unitary. That I agree. The
So you
reflection
are
is
saying
not
that we have only CT operator and turn some rotation operator. But
I don't know.
If it's -1 each, then you can't do that.
okay, so another thing, rotation means you can rotate in any direction, right? Not just x goes to minus.
Ha, you're a very specific rotation.
You are this very specific rotation. I
Ha,
mean, just
that
just
I'm-
reflection. That's
Ha.
the reflection, of course, right? So this does not compute to x to, I mean, some e to the I theta x or something. I mean, not any rotation.
Right, you see, it is I pi x.
Just
I mean,
just
like literally
I pi x,
Ha.
exactly. So this is just a reflection. I mean, x goes to minus x. So it's very special. I mean, in sense, in this sense. Okay, so now I'll come to the approach of this one and Wichmann.
Then, Suchetan, can I clarify something from before? Like this J, right? You said change takes time to minus t, right? But J also takes to the x to minus x. So by that logic, wouldn't phi dot have got two minus signs and would have had a relative minus sign compared to how delta works, right?
Yes.
Because delta only changes to the other side,
Right.
but it's not changing flipping sign of time. So hence, since in your convention, since delta and j ka action on phi dot seems to have both gain a minus sign, seems like they are inconsistent to me. Because j flips time, and then we were evaluating 0 time. But so phi dot, the dot gets a minus sign.
Yes.
Flipping the direction of derivative of time.
Yes.
Not time. So just as Suchetan
No, j is flipping the direction of derivative of time. But further phi dot, he said phi dot has an implicit time flip, direction flip when you just go to the other wedge. J seems to be doing both.
Yes. Yes.
So hence, shouldn't the delta and j ka action have opposite time parities for phi dot? Because both are happening for j.
No,
Only one is
delta
happening
to
for
half.
delta.
Specific delta to the half. I mean,
Huh?
this for delta to the power half, right? I mean,
Yeah, but the minus sign there was due to the excess flipping.
Right.
Here the minus sign is due to excess flipping and the t
T goes
flipping.
to flipping. Yes.
But both seems to give only one minus sign, which I'm saying is sounds like inconsistent. Naively.
No, what is the inconsistency? I'm sorry. No, but ace acting on phi dot is this right? This phi dot.
I'm saying like, I thought I get a minus sign for x flipping, I get a minus sign for t flipping,
Yes.
because it's a derivative. For j action should have given me two minus signs
Yes.
on phi dot.
Yes.
Two minus signs is a plus sign, no? That's all I'm saying.
2 minus sign plus sign for which? I mean,
What?
and these 2 minus signs, right? These 2 minus signs. Phi dot. So, and delta to your half is phi dot is 2 minus sign. So ace phi dot is just plus sign, right? That was because ace phi dot is just phi dot.
Are you look at delta, what is the time parity sign, time parity of phi dot under delta, what's the time parity of phi dot under j? They should be, in delta you get to flip the sign of phi dot only because of x flip.
Yes.
You said you get one sign. But in j, you have to flip the sign once because of x flipping and once because of time flipping. And it seems to give you only one minus sign in either cases. Okay, maybe we'll discuss later. It's okay.
Yeah,
Thanks.
yeah, please. But I don't understand what you are saying. But all I am saying that the property of this J just follow from these 2 points. Okay. That you agree, right? That yeah, that I just that I just wrote down from these 2 points, S and delta to the half.
I just want to say I was wrong actually. Like it's right that it's a discrete transformation. Like because why will I mean so? If 2 of the coordinates goes to minus, then one can show that it's rotation.
Yeah. So yeah, so from path integral, what we find is that this delta omega is basically k, sorry, e to the power minus k, where k is the boost operator, and j is CRT operator. And we see that this also follows from the fact that if we actually factorize this h equals to hr cross hl, then we get this delta from this in this approach. Okay, so where for this case we know that delta is rho r cross rho l inverse, which basically means that it is e to the minus kr minus kl. So rho r is basically e to the minus kr. It is kl. But now, what actually originally that what is shown by Bisognan and Wichmann is that you can actually derive this k, I mean this delta, without assuming this factorization or without going to any path integral approach. You can directly find this delta. But but I don't know the actual proof. But what in Witter's lecture he actually gives some argument to find why this is true. Okay, so he actually said that suppose we already given that j, we have a unique j which is CRT operator, which follows from this property. Now we want to prove that should I discuss this or should I go to any other thing? I mean, do you want to? I mean,
what will be the point of this? Meaning, how long is that?
Sorry.
How long is this derivation?
How long?
Yeah.
Yeah, it will take. I mean, okay, yeah. Let me just then. I'm just describing it briefly. Okay, yeah. So he just want to show that that this is the delta operator, that is the half operator, which actually takes any a to the power a where a goes to okay. So what we
you-
want to show is that
You had done earlier use the path integral. Now you want to show the same results using this theorem.
yes. So should I
Prove this is the theorem, right?
huh?
Is this a theorem? Or
No, this is a theorem. Yeah, his result is that to show that without using the path integral, he is the original. He is the first one who show that this delta for this case is actually the boost operator. Okay. So, but without using any path integral and so on.
Exactly.
So yeah. So I mean, I don't want. I mean, if you want, then I can discuss. But if you don't want, then I can go to one. Hmm? How? Sorry.
average knowledge condition.
ANEC.
Yeah.
Yeah, I can discuss it. I mean, there's modular inclusion. I can also discuss
Can
it.
you fit all these?
I mean, what is the plan for you? What was the
Yeah,
plan?
I
that
mean,
you-
I think that I thought that it should be. I mean, I can discuss this within 1 hour, and then I can discuss. I mean, in question, but so in reality it does happen. But so it's up to you what you want. I mean, yes. If you want this, I can discuss this and I end this, or if you want that, I can discuss modular inclusion and I can end. I can't discuss both, of course.
So let's take a poll then. Poll.
Okay, so actually there's no short talk today, so there you may get half an hour after the tea. Is there any tea, by the way? I mean, they usually call to bring. I don't see any. Okay, so there is no short talk today, so you can take half an hour after the tea if you wish.
So
If there is tea. What you don't want to do.
No, I mean, yeah, and if everyone is, then I can continue. But yeah,
Maybe-
it's okay. So
Maybe you can go through this sketch, both of them, and if we have questions, we'll ask.
yeah, so the point is that what he want to do is like he said that. So in path integral approach, we see that this delta to the has is actually this boost operator, because due to this path integral, the angular quantization thing. But now he want to show that this is indeed this boost operator without using this path integral, but using some holomorphic statement. Okay. So this is just some math. Okay. So here suppose we take A to be by So these all is inserted at the right ways.
Phi is?
Hmm?
What is phi?
Sorry.
Product of fields. Are they smeared?
Hmm?
Are these fields smeared or? Just
Yeah, you can think this of smeared, but let's just think that it's not smeared. So for this case, but if you actually do this, you have
Okay.
to do some smeared operator. But for the sake of simplicity, just assume this. So okay, and next thing is that you choose this pi, which is the set of points pi to be such that for I used to that every point is spatially separated from each other. Okay, I mean every point is spatially separated from each other. Also, there is an ordering of this point. Okay, so ordering means that we are saying that xi, xj. This is just a convention. I just choose these points in the following way, that this is in this way, x1, x2, x3, and in the following way, and
Okay,
t1
so
to.
only in the x, from x you are ordering.
Huh?
Only for x you are
No, for j greater than I, xj greater than xi. And this means that, okay, also this space, since it is spatially separated, this is the ordering I just choose. I just choose this ordering, okay. So now point is that for S belongs to R, so a boost operator, a boost operator maps any point like T prime So for any boost operation, for boost parameter eta, we know that the scalar field, any scalar field, just transform like this. Also k 0. Now this means that 2 pi r. So I am just okay, but I am just action. I'm under the boost. How this A changes at this point. So now the point is like that. Okay, from here you can see that if S is the so this is I mean this S is actually I eta. Okay, so if point is that if eta can be analytically continued to I by 2. Then if you just put here the I eta equal to I by 2, then you can see that this x prime is basically minus x. Okay.
Yes.
So
You started with S belongs to R.
hmm?
Started with S belongs to R. So how valid is it if
no,
we
that is the point, that if I can analytically continue to this, I mean from this real to a complex plane where the imaginary part is I by 2. I mean it is valid only for, of course, as you said, it is only valid for real S. That is the point. If I can take into an imaginary value. I mean, if I can analytically continue to imaginary value with I by 2, then we can say that that's true. So the point of basic London Wishman is to prove that the range of the holomorphy of this, that this thing, if we denote this as f of x1 xn, this thing is actually holomorphic. He proves that this thing is actually holomorphic for the range I mean that for 0 to imaginary of eta half. I mean, any function can be analytically continued if it has analytical continuation. I mean, it can, if it can be analytically continued too. Yes, that is the point. Yeah, and he actually proved this. So can I go to this proof? I mean, that so in the so what I mentioned in the first summary, that in the previous day, what I mean, what's the name? Debangshu has showed us that the zeta z to the power is acting on A omega. This is holomorphic for sorry z, yeah. If imaginary z, so we are saying that if delta is the boost operator, we have to show that this boost operator is also holomorphic in this way. Then delta is the k, and for k equal to half, this is the boundary of the holomorphy. So we can use the k equal to half. I mean, this imaginary of z is a half, and we can get this result. Okay. So that is his. I mean, that is his sketch. I mean, whole point. To show his point is to show that this thing is holomorphic between this thing. Okay.
And eventually you take one particular point where it becomes k. The boost generator, right? And hence it should be valid.
Yes, yes.
Okay.
Exactly. But to prove this, I have to prove another theorem, and so do you need this? I mean, this proof, or do I? Yeah. Yeah. Just you have to prove that it is a holomorphy, but it is not easy thing to prove this holomorphy, because you have to use another thing. But okay, let me. Huh?
Let you.
So what do you mean? I mean, what do you want?
Are you saying that the Bisogno-Wishman statement or theorem, whatever you wanted to show, is concluded?
He's saying that the thing that involves.
Yeah, this small step that you will take time to prove, don't prove it.
Yeah.
Yeah.
And then after that.
Go ahead on this theorem. What happens? So you wanted to show, I mean, I wanted to see how this k comes again, using the proper theorem.
No, what he shows that if
sorry, what? Chai is ready. Stop.
But I think it's done. Just you tell the sentence.
Yeah.
Okay, so I'm just saying that.
It's done.
Okay, ठीक है.
Yeah. Take one particular value, imagine part of that equal to half. There you can moderator. What moderator?
No.
Yeah. So you can take on the mic.
Yeah.
This k is so using path integral, you showed that different certain form of J delta.
Yeah, from the path integral.
Left after the T you want to discuss, or are we finished for today?
Yeah, but